Welcome. In this video, we're going to continue our discussion on rectification. Last time we had a discussion on a half-wave rectification where you had two diodes, and if you had a power supply which supplied this kind of input, what you would observe as an output is that you would have two peaks, and only part of the wave will survive. So one half will be chopped off and only one part will survive. Hence we call this a half-wave rectifier, or this is a half-wave rectification. And keeping with our conventions from the previous video, that is the red part of the cycle is going to signify a counterclockwise flow of electrons through the circuit, and the blue one will represent a clockwise flow of electrons through the circuit. Remember, we are focusing on electrons, not on conventional current. Again, we would like to redeem this kind of a dead time because we would like to operate as efficiently as possible. Okay, so how can we overcome these kinds of dead spots where we're actually not producing any X-rays because the power supply here, electrons are not able to flow? Well, there's another way called the full wave rectification. This one actually corrects for, it works for all cycles. For all parts of the cycle. It's not only keeping the half of the wave, but it keeps the entire wave, which means our exposure time can be reduced. Okay, so typically again, the supply from the power supply, or the signal from the power supply looks like this: two cycles, two waves. And what we have here is what we call a full wave rectifier. The key is that it has a particular orientation. So here's the experiment. We are going to supply some input and we're going to follow the electrons through this configuration of these diodes or electronic valves. And we are interested in what are we going to measure. In which direction will electricity flow through this voltmeter? The V here refers to a voltmeter. It's what we're measuring. Okay. Before we get there, I would like to give us a bit of a heads up. The way to follow the electrons, there are two important rules. The first one is that electrons will always flow from the negative pole to the positive pole of the circuit. That's how electrons will flow. And diodes will only allow one direction, flow in one direction. It will not allow direct flow of electrons in two directions, but only in one. So let's consider the situation where electrons, or the cycle of the power supply, the cycle of the power supply is on this circuit or cycle, this part of the half wave. So counterclockwise, let's consider. So here's our power supply. Because we're considering the counterclockwise flow, in general, electrons are going to exit from the power supply, and then they're going to go through this circuit. And by the way, this junction here, this curvature means there's no connection, but one wire goes underneath another. So this is not a connection. Okay. So electrons are going to come in here and go all the way up here. Now, remember the rules of the diode. Electrons, will they be able to go through this? Well, look at the orientation of the diode. Electrons will not go in the direction of the play button. They can only flow the other way. So, given these two options, which direction are the electrons going to take? Well, they're going to take this one. And when they get to this junction, they have two options. They could either go this way or down that way. But look at the orientation of this diode. Again, electrons will not be permitted to flow up that stream, so therefore the electrons are going to flow this way. And they're going to go over the loop, go through this way. Notice what the direction of the electrons through the voltmeter, it's in this direction, upward. And then they're going to continue, and when they get to this junction, now, it's possible for electrons to go either this way or that way. But remember, when they get over here, what they're going to feel, if they were to go down here, yes, they will be permitted to go through the diode, but notice they will be approaching other electrons. What do we know about like charges? You have electrons coming in here, and would these electrons choose to meet with these ones? No, because like charges are going to repel. Therefore, these electrons are going to go up this stream. And the same goes when they get over here. They have the option of either going this way or up. Again, there's electrons still moving up here. So the electrons that are at this junction will not opt for this by arguments of electrostatics. That is, the electrons will favor to move that way, and then they will close the circuit and return to the source. The key here is that when we have the counterclockwise flow of electrons, look at the direction of electrons through this voltmeter. It's this way. It's upward. Let's contrast. Suppose we were to reverse the polarity. That is, we were going to consider the clockwise flow. In other words, now electrons are not exiting the source going down. They're going to exit the source going up. Let's consider what that looks like. Okay, this is what the next slide has for us actually. So if electrons were exiting the source and going this way clockwise, this means we're on the blue part of our cycle. So electrons are going to exit the source and get to this junction and make their way up here all the way to this point. Now, when they get to this junction, which direction will they choose? They could either choose this way or that way. Notice the orientation of the diode. It's such that it prevents or it impedes the flow of electrons down this way. So the electrons are going to take the path with least resistance, and that's that way. And when they get over here, notice the orientation of this diode. Again, electrons cannot flow downstream here. So the electrons are going to flow this way, and then they're going to make it over the loop and go over. And now look again. The voltmeter, look at the direction of the flow of electrons through the voltmeter. It's still up. Even though the polarity is different, the flow of electrons here is still one way. Okay, and then let's go further. Electrons are going to get to this junction again. Now, when they get to this junction, it is possible for them to either go this way because the orientation of the diode allows them. Same thing here. But remember, there's more electrons here. So when these electrons get to this point, they will not favor this direction because of repulsion. Like charges are negatively charged particles, so these electrons would rather take this direction over that one. Okay, so they're going to go over here, and the same thing goes when they get here. They could either go upstream or downstream. Because there's more electrons on this side, or there are electrons on this side, which are still flowing in, the electrons that are at this junction will not favor this direction. And that's not because of the diode, but that's just because of electrostatics. So therefore the electrons at this junction will flow down and then return back to the source. And the key takeaway here is that by virtue of this orientation of diodes, It doesn't matter what the source is supplying. The flow of electricity through the voltage is always up. Look, in the blue cycle, it's flowing up, and in the red cycle, it's flowing up. What this means is that what we're going to read on this voltmeter, if we supply a red cycle, what we're going to read is going to be a red cycle that's up. In other words, the electricity here is going to flow up, and in the blue cycle, the electricity is still going to flow the same direction, so we're going to get another peak. And same thing here, when we get to the red cycle again, we're going to get another peak. And instead of going in the wrong direction, instead of electricity flowing that way, because of the orientation, it's going to flip up this peak, or the blue cycle. So the point is, no matter what the source is doing, it's alternating on this side. The current on the source side is alternating, but what we read on the voltmeter is direct. The current here, or the voltage here, is always positive. On this side you have a positive and negative, or if you like, clockwise, anti-clockwise, clockwise, anti-clockwise, clockwise. But over here, on this side, it's always anti-clockwise. The current will always go up through the voltmeter. And that's what we use. Your modern day X-ray machines, they use a full wave rectifier, albeit with a couple of changes, because one of these undesirable things are these drops here. So sometimes you might put in a high frequency generator where these peaks or these drops here are not so deep, but actually your output oscillates very close to the maximum kVp you set. Other ways, some people, they put in a diode, and a diode avoids this kind of a dip. Because when you have this kind of a dip, that means you're not operating at your full voltage that you've set. When you set a kVp, what you are deciding is this peak, but you're not all the time operating on this peak, unless you mitigate by introducing other things like, as I mentioned, a high frequency generator or some kind of a capacitor. Okay, but in general, this is what a full wave rectifier is. We'll stop here. See you in the next one.